Today, we have a refrigerator, and you can see this small box on the backside. When you press it like this using any tester, it pops up, and now you can see the PCB. After taking it out, you'll notice a few connectors, red, blue, and white. The red and blue wires are for the main power supply, while the white wire is used for the door switch. Similarly, if you look at another small connector, it also has 3 wires, red, green, and black. The red wire supplies 12 volts, the green wire is used for the violet light, and the black wire operates the fan. As you have seen, this PCB is mounted on the back side of the fridge. It takes 230 AC volts to convert into a 12-volt DC power supply. It is used to operate the light and fan inside the fridge. Now I'll explain how this PCB works, what components it contains, and where and how much voltage should be present. This will make it easier for you to repair it. First, let's take a look here where the supply is written. The supply should always be connected correctly to extend the life of the PCB. The first pin is the line, the center pin is neutral, and the third pin is labeled as door. I'll explain later why this pin is labeled as such. When electricity flows to these pins, I have installed a 180 ohm resistor here. Originally, 220 ohms resistor was used, and this is a current limiting resistor. But since I only had an 180 ohms resistor, I installed that instead. This is a 5-watt resistor, which is often prone to failure. After this resistor, there's a ZNR installed, which is used for voltage protection. If the voltage exceeds 250 volts, the ZNR will blow, and as a result, the resistor may also fail. This prevents the system from further damage by blocking the supply. Next, there's a capacitor, which is used for filtering. Following that, there's a line filter designed to control voltage spikes. After this, the system moves forward into a circuit with 4 diodes. These are not ordinary diodes. They form a rectification system. Rectification converts AC supply to DC, slightly reducing the voltage during the process and converting it into DC for further use. Here, you can see a 22 microfarad 400-volt capacitor installed, which smooths the DC electricity. After the conversion, you should get around 320 volts. If the voltage reaches 320 volts, the system will operate correctly. If it doesn't reach this voltage, the system will not function properly. Here, you can see some resistors and a capacitor installed, along with a diode. These diodes are used for protection. If a heavy voltage spike occurs, the diodes will short circuit, helping protect the PCB from damage. Now, the capacitor you're seeing is connected to the optocoupler, which is located here. The optocoupler is connected with a diode and is connected in series to the door switch. Because of this connection, when the fridge door is closed, the optocoupler is activated. When the optocoupler turns on, it triggers specific functions that I'll explain further. Now, when the electricity comes in, it reaches the switching IC, which is Viper 17H. If this IC fails, the entire PCB will stop working. If the high side is getting power, but the low side is not, it could indicate an issue with this IC. In such a case, replacing the Viper 17H IC will likely resolve the problem and restore proper functioning to the PCB. Now, let's explain the switching IC in detail. Pin 1 is the ground pin, which is connected to ground, and it serves as the source pin. Pin 3 is for current limiting. A 223 ohms resistor is connected here to set the current limit. This helps control the current flow through the circuit. Pin 2 is the VDD pin, which receives the power supply. This provides the necessary voltage to power the IC. Pin 4 is connected to the optocoupler. This means feedback is generated here from the optocoupler, which controls the switching operation. Pin 8 is used for the threshold voltage setting. A capacitor here should have 10 volts. If the voltage is only around 6 volts, it means the voltage supply is insufficient, which will cause the IC to turn off the entire system to protect it. So, to ensure proper operation, this capacitor and diode must maintain around 10 volts. When the system goes into the drain, you should get 320 volts on the positive side. If this voltage is present, the chopper will start functioning properly. If 320 volts are not present, the chopper will not work. Once the 320 volts are available, the chopper will begin to operate, and this will enable proper functioning of the system. On the low side, you should expect to see voltage, but you will notice it is not present on the anode side. You should receive voltages on the cathode because this is a snubber or flywheel diode. You will find many other names. It prevents positive voltages from moving back toward the chopper. On capacitor C5, you should have 12 volts. Similarly, capacitor number 3 should also have 12 volts. For the remaining capacitors C12, C13, and C14, you should see 5 volts across them. C8 should also have 5 volts. After these voltages are correct, the system will proceed to the microcontroller for further operation. Let me explain the role of the microcontroller in this system. When the door switch is turned on and off in the series, the optocoupler plays a key role in controlling the system. If the door is open, the system is off. The supply will not reach the optocoupler, causing it to stop functioning. In this case, the microcontroller will turn the fan off. Afterward, when you close the fridge door, the switch will also be closed, which will activate the optocoupler again. Once activated, the microcontroller will start receiving voltages to understand that the door is closed. The microcontroller will perform two tasks. 1, it will turn the fan on. 2, it will activate the violet light. Here's how the feedback mechanism works in this system. An optocoupler is installed along with a reference IC. The feedback loop starts when the reference IC generates a voltage, which turns the optocoupler on. When the optocoupler is on, its emitting diode gets activated, causing the NPN transistor inside the optocoupler to conduct. This transistor allows the supply voltage to pass through, effectively turning on the system. The feedback from the optocoupler also ensures that the system remains in operation by providing a stable voltage supply. Once this feedback mechanism is established, the system starts working correctly. The reference IC ensures that the supply voltage is appropriately provided, and the optocoupler controls the flow of voltages to power the necessary components, allowing the whole system to function as expected. Finally, let me explain the function of the small connector pin 1, which is the ground pin. Pin 2 provides 12 volts, which is used to power the violet light. The last pin is connected to the fan, and it is through this pin that the microcontroller controls the on-off operation of the fan. In summary, the small connector allows the microcontroller to control the violet light and fan by providing the necessary power and switching them on-off as needed. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.